right, here's day 56 of geometry. So we have a square pyramid is a pyramid with a square base and 4 triangular lateral faces, lateral meaning the sides. So we could draw our square and then we'll just do a point up top for them all to connect to. So pyramid is just going to be kind of like a prism where you have a shape, except instead of connecting to that same shape lifted up, it's going to be connecting at one point up top. So in this case, it's a square pyramid. The slant height is the distance from the vertex. So the vertex meaning the top point up here of the pyramid along a lateral face, so along one of these faces, right, so like this, to the midpoint of a base edge. So it's talking about this line, right, connecting the midpoint of the base edge. So this is the base edge to the vertex. The slant height is 10 centimeters and an edge of the square is 12 centimeters. So of the square, that's this down here, right, 12 by 12. What is the altitude of the pyramid? So the altitude would be if you drop the vertex straight down to the middle of the square, so the middle of the base. And the way we could find this, we know that the slant height will be longer, right? It's not as direct as just dropping straight down, but it will make a right triangle because we know the altitude is going to be perpendicular to the base. So if I redraw that over here, we've got our height, what we're solving for, again, the altitude. We've got this leg is going to be half of the base, right? Because it's the midpoint, or it's the middle of the square. So half of 12 will be 6. And then this would be our slant height. The hypotenuse is the slant height, which is 10. All right, so there's 2 ways you could do this. You could do the Pythagorean theorem and solve for h. So we do leg squared plus leg squared. So h squared plus 6 squared equals 10 squared. Just make sure you set that up correctly. And then do 6 squared is 36. 10 squared is 100. We'll subtract 36 from both sides and we get that h squared equals 64. And then the square root of both sides, right? You don't have to worry about the negative solutions in geometry because you can't have a negative height unless you're talking about going underground or something. And that would be that the height is 8, our units per centimeters. So that's one way you could do it. You could also realize that if it's a right triangle, it might be a Pythagorean triple. And in this case, 3, 4, 5, our most famous Pythagorean triple, is just being scaled up by a factor of 2. So 3 times 2 is 6, 5 times 2 is 10, which means that the other leg should be 4 times 2, which is 8. And so that's just a 3, 4, 5 scaled up by 2, which would also get us to 8 centimeters. So that's our answer. Next, we have to find the area of a regular 36-sided polygon inscribed in a circle of radius 20 centimeters. And then from there, if this polygon were the base of a right prism just meaning that basically the altitude is perpendicular, or like you lift it up in a way that's perpendicular to the base. So the height will be perpendicular to the base, and that altitude would be 50, will be the volume. So we start by just finding the area of this base. So we know it's a 36-sided figure. I'm not actually gonna draw 36 sides. I'm just gonna sketch it with a bunch of lines. It's probably gonna be more like some kind of octagon or nonagon or something, right? But imagine there were 36 sides there. So if we find the area of this 36-sided shape, and we'd have to multiply that by the height of the prism. And by the height of the prism, I'm talking about this 50 centimeter altitude that they're giving us. So not the height of any triangle or part of this 2D shape. So that would give us the volume of the prism. I think it's called like a hexatridecagon, something like that. Usually you just call it a 36-sided polygon. Now, if we want to find the area of that 36-sided polygon, that would be equal to 36 times the area of one triangle if you divide it up into 36 triangles. So we could divide it into 36 triangles. Again, I didn't actually draw the shape there, but it's the same way that you would solve the area of an octagon or a decagon or a dodecagon, right? Any shape. You just have to use trig to find the base and the height of one of these triangles, then use 1/2 times base times height, the area of a triangle, to solve for it. And then you multiply by the number of triangles. Because if it's a regular shape, which this is a regular 36-sided polygon, then all of those triangles will be the same size. They're all congruent. So first we have to find the angle up top so that we can use that to do our trig. And we can do that by knowing that the entire circle, like the circle I just drew, is 360 degrees, and we're cutting it into 36 equal slices. So we could divide it by 36 and we get 10 degrees. All right, so each of those angles up top is 10 degrees. So if I redraw one of those triangles, we have 10 degrees up here. They said that it is inscribed in a circle of radius 20 centimeters. So the 20 centimeters are these blue lines I drew, which are not the altitude or the base of the triangle, but if you divide it into a right triangle, which with an isosceles triangle, you can drop an altitude and it will, right, an altitude means it's meeting at 90 degrees, it will also cut the angle up top in half and the base in half. So this would be half of the base over here, And then you also have half the base over there. And again, it's cutting that angle up top in half, so 10 becomes 5 over here and 5 over here. All right, so now we actually have a right triangle where our angle is 5 degrees, and we know the hypotenuse is 20. We can use some trig functions now, and we know that we need to find the opposite, which is base over 2, and we need to find the adjacent. We're given the hypotenuse. First, if we try to find this opposite, the base over 2, we would use sine, because we know that sine of theta is equal to the opposite over the hypotenuse. And in this case, our theta is 5 degrees. So sine of 5 degrees is equal to the opposite, which we said is base over 2, right? Half of the base of the entire triangle, over 20. 20 is our hypotenuse from right there. So that would be how we would get our base. And now just to get the base alone, you multiply by 20, and then you multiply by 2, which is the same thing as multiplying by 40. Right? 20 times 2 is 40. So that gives us that the base is equal to 40 times the sine of 5 degrees. All right, so that's our base. Now we need to find the height. And if I label the height on the picture, it's this altitude that we drew right there. Right? It's adjacent to the 5-degree angle. It's not the hypotenuse, but it is touching it. So we'd say, in this case, the one that uses adjacent and hypotenuse is cosine, because cosine of theta is equal to adjacent over hypotenuse. So in this case, the cosine of 5 degrees is equal to the height of the triangle. And I do want to specify that I'm talking about the triangle's height, not this height of the entire prism. The height of the triangle over this hypotenuse, 20. Now to get the height alone, you just multiply by 20 on both sides. And that gives us that the height of the triangle is equal to 20 times the cosine of 5 degrees. We have our height and we have our base. Both of those are necessary to find the area of the triangle. The area of the triangle is equal to either base times height over 2, or you could write it as 1/2 times base times height. So now I can plug that in for the area of the triangle. Area of the triangle is equal to 1/2 times, base is right there, so that's times 40 times the sine of 5 degrees. Note that I'm not rounding yet. You could round it and just round farther than what you need, but I usually just don't round until the very end. So I'll leave it in terms of sines and cosines or tangents if you have them. Times our height, which is 20 times the cosine of 5 degrees. This all is the area of the triangle. And then we're going to plug that in to this formula here. So 36 times that area of the triangle. That would give us the area of the entire hexatridecagon, right? The entire 36-sided figure. And then you have to multiply that by the height of the prism, which is 50 centimeters. So I'm going to make some space for myself to do this math here. I'm going to go straight to the volume of the prism. Volume of the prism is equal to the area of the 36-sided figure. Now we know that area of the 36-sided figure is 36 times the area of the triangle, right? Now the area of the triangle we just wrote here. Again, I haven't rounded it yet, but I can just copy this exact expression here, paste it down, right? You could also just rewrite it if you were not being as lazy as I am right now. Now we've got 36 times the area of the triangle, which is the area of the polygon, and we have to multiply that by the height of the prism. We know the height of the prism is 50 centimeters, so I'll just plug that in at the end. So now this is going to give me my answer. So I just have to go grab my calculator, and we've got 36 times 1/2, which you could just do 36 divided by 2, times 40 times the sine of 5 degrees, and make sure you're in degree mode, times 20 times the cosine of 5 degrees, times 50. And that gives me that the volume of the prism is about equal to 62,513.34396, and it keeps going. And do they say how to round it? They do not say how to round it, so I'll just say it's 62,513.34, and our units are centimeters, so it's centimeters cubed. Right, so that's your volume of your prism. Again, you just found the area of the shape, right? In this case, even though it's 36-sided, it's the same steps you would do for any regular polygon, at least any regular polygon bigger than a square. And you know, that number does seem very big, but it does kind of make sense. Just volumes are very big, and especially if we're measuring it in cubic centimeters. Think about a 1 meter by 1 meter by 1 meter box, right? So it's just a cube that's 1 meter in each dimension. That would actually be equal to 100 centimeters by 100 centimeters by 100 centimeters. Which means you could do 100 times 100 times 100, which is 100 cubed, or 10 squared to the 3rd power, which is 10 to the 6th power, which is 1 million. So what that means is there are 1 million cubic centimeters in a 1 meter by 1 meter by 1 meter box. So that's how many could fit in there. So cubic centimeters are much smaller, and once you're talking about a 3D space, a lot of them are going to fit into a space. So this is significantly less than a 1 meter by 1 meter by 1 meter box, so it's actually not that many cubic centimeters. When you walk into Weaver Hall, there are 2 large regular octagonal pillars. The edges are 6.5 inches, and by that they mean the edges of the base, right, the edges of the octagon, and they are 9 feet tall. I specify that because technically, right, the height could be considered an edge, right? Especially, think over here, even these would be edges, right? An edge is any line that's connecting a vertex to another vertex, so connecting 2 vertices, or 2 adjacent vertices, I should specify. So if I were to draw this octagon, I'll just make it look kind of like a stop sign. Each of the edges are 6.5, and our height is 9. Although note that it's 9 feet tall, whereas the edges are in inches. So let's start right off the bat, not getting caught with that. Always check your units. This is something that you could easily get the answer wrong after doing all of the hard steps just because you forgot to convert it into inches. So if we have 9 feet, and you want to convert that into inches, we multiply by 12 inches over 1 foot. Right? That's basically something divided by itself, so it doesn't change the value of it. But the feet cancel out. You get 12 times 9 is 108 inches. All right, so I'm going to make that 108 inches, just so we note that and don't forget it later in the problem. Now, if we want to find how much granite was needed to build these pillars, we're essentially just finding the volume, right? The volume of granite that was needed. So what's the volume in those pillars? And we do that similar to the last problem. So the volume of the pillar is equal to the area of the base. So in this case, the base is an octagon. So we'll say area of the octagon times the height of the pillar. Also, you call that the altitude of the pillar. So we know the height of the pillar is 108 inches. We just need to find this area of the octagon. And as we've been doing with a lot of these areas of polygons, and as we just did with the 36-sided polygon, we're just going to do 8 times the area of the triangles that make up that octagon, right? It's a regular octagon. You could divide it into 8 congruent triangles like this. And now to find the angles in that, we would just do 360 degrees divided by 8, which gives us 45 degrees. So each of these angles up top is 45 degrees. And if I were to redraw one of these triangles, we get 45 degrees up top. We can drop down in altitude, which will cut the base in half. So we have 6.5 for the entire base. If we cut it in half, that will be half of 6.5 is 3.25 inches. Your base there. This will make a right angle, and it's going to cut the angle 45 in half, which makes 22.5 over here, 22.5 over here, right, in degrees. Now we have the base. We don't need the hypotenuse. All we need to find is this height here, right? Because the area of the triangle is equal to this base times height of the triangle divided by 2. Base is already known, and I guess I wrote the base as if it's this 6.25, but our base is actually 6.5, right? It's the entire base. And now to find the height, we would need to use tangent because we have the opposite of the 22.5 degrees, where there's across from it, and the height is the adjacent. So I'll write that as the tangent of 22.5 degrees is equal to opposite, so 3.25, divided by the adjacent, which is the height. So now we want to get the height alone. So we'll start by multiplying both sides by the height, which gives us just 3.25 on the right side, and on the left side, it's height times the tangent of 22.5 degrees. And now to get the height alone, we just divide both sides by the tangent of 22.5 degrees. All right, so that will give us that the height of the triangle is equal to, well, this cancels here, it's equal to 3.25 divided by the tangent of 22.5 degrees. Now we can plug this in for our area of our triangle, and we'd say the area of the triangle is equal to the base, so 6.5, times the height, which is 3.25 over tangent of 22.5 degrees, what we just did. And this is all divided by 2. Right, so that's just the area of the triangle. Now, if we want the volume of the pillar, which is ultimately what we're trying to find, how much granite was needed for the pillar, so how much total volume is the pillar, we go back to that equation up top, which is the area of the octagon. Now, for the area of the octagon, it's 8 times the area of the triangle. So 8 times what we just did. So again, I'm just going to copy the area of the triangle. You can also just rewrite it, but this is saving a little bit of time. 8 times 6.5 times 3.25 over tan 22.5 all over 2. And then we have to multiply that by the height of the pillar in inches, right? So keeping our units constant, found that that was 108 inches. Right, so don't write 9 there, because then you're going to be off by a factor of 12. So now we just type this into our calculator. I'm going to write 8 times 6.5 times 3.25 divided by parentheses tangent of 22.5, close parentheses, like of the entire denominator there. Then divide that by 2 and then multiply by 108. And it gives me the volume of the pillar is about equal to 22,032.11297. Again, let's round, and that would be in inches cubed. So we can again round that to the nearest hundredth, and that would give me 22,032.11 cubic inches. And that number seems really big, but it's actually 50 times smaller, or about 50 times smaller than just a 1 meter by 1 meter by 1 meter block of granite. All right, so the last question we have here, the Great Pyramid of Giza was originally 483 feet tall, and it had a square base that was 756 feet on each side. So we can draw a square, 756 by 756. Our height is 483. So the vertex, they all go to the vertex. And if you drop down in altitude from there, it would be 483. Now, the volume of a pyramid is equal to 1/3 times the area of the base. So in this case, it's the area of the square times the height, right? So the height of the pyramid. So in this case, if we want to find the volume of that pyramid, it's 1/3 times the area of a square is side squared, or side times side. So I'm just gonna write 756 squared, and these are both in feet, so we're already good, times our height, which is 483. All right, so that's gonna be our volume of our pyramid. It was built from a rectangular stone, or from rectangular stone blocks measuring 7 feet by 7 feet by 15 feet. So 7 by 7 by 15. Okay. Now if you want to find the volume of a block, just be a rectangular prism, so length times width times height. In this case, it's going to be 7 times 7 times 15. These are still in feet, right? So our units are consistent there. All right, such a block weighs 70 tons. So each of these blocks, that's 7 by 7 by 15, would be 70 tons. So I'm going to start by finding the volume of one block. It's just 49 times 15, which is 735. Right, that's cubic feet. The volume of the pyramid over here, this should end up being a whole number because I think 43 is divisible by 3. That's 161. So we have 161, which is 43 divided by 3, times 756 squared, which gives us an enormous number, 9201729.6. Can rewrite that as 92,017,296. Again, this would be feet cubed. So if we want to figure out how many blocks go into that, right, we could say the number of blocks is going to be equal to the volume of the pyramid divided by the volume of one block. Again, that's this number, 92,017,296, divided by 735, which gives us 125,193.6 blocks. All right, so if we know there are that many blocks and each block has a mass of 70 tons, then we just multiply 70 tons times this number of blocks here. And so our mass would be equal to the number of blocks times the mass per block. And mass per block is 70, as they said. So we would say our mass is equal to 125,193 blocks times 70 tons per block. And in this case, the blocks will cancel. We'll just get 125,193.6 times 70, which is equal to 8763552, which is equal to 8,763,552 tons. That's our mass. So approximately how many tons of stone were used to build the Great Pyramid? That'd be approximately 8,763,552 tons. And the volume of a pyramid is 1/3 the base area times the height. All right, so that's just this formula that we did right here. A lot of times you'll write it like this. And if you see a capital B, that generally means you're talking about the base area, right? The area of an actual face. Whereas for like an area of a triangle, you would just do that. So 1/2 times base times height. In this case, this little b just means like one side of the triangle or of the shape. So for volume, you're using that capital B. Well, I think that's the last question here. If you have any questions, or if you think I messed one of them up, or if you had a better way of doing it, feel free to comment below. But this would be a fairly efficient way of getting through these 4 problems. All right, thank you.